The ocean looks like one connected body of water when you look at a map, but in certain places around the world, you can see something that doesn't make sense. Two different masses of water meet, and they refuse to mix together. A visible line runs between them. It looks like an invisible border cutting through the sea, or a transparent wall standing in the middle of the water. On one side, the ocean might be dark blue. On the other side, just a few meters away, it turns turquoise or grey or pale white. This shouldn't happen. Liquids blend together when they meet. Pour cream into coffee, and it spreads immediately. Drop ink into a glass of water, and it dissolves in seconds. That's what fluids do naturally. But here, massive bodies of water flow right next to each other for years and keep their separate colors. The boundary between them stays sharp and visible day after day. One of the most dramatic places to see this is in the Gulf of Alaska. Ships passing through this region often slow down so passengers can come out on deck and photograph what they're seeing. On one side of the vessel, the water is dark blue, almost black when the sunlight hits it at certain angles. On the other side, the water turns pale and cloudy, like someone poured milk into the ocean. Between these two bodies of water runs a band of white foam that stretches as far as anyone can see. It looks like someone took a piece of chalk and drew a straight line across the surface of the ocean. The two colors stay completely separate, even though waves are rolling back and forth across the boundary. The pale water comes from glaciers melting along the Alaskan coast. As the ice breaks down and flows toward the sea, it carries almost no salt because glacier ice is made from compressed snow. But it carries something else along with it, which is fine powder ground from rocks. Glaciers move slowly across mountains for thousands of years, scraping against stone and pulverizing it into dust, so fine that it stays suspended in the water instead of sinking. This rock powder is what makes the glacial meltwater look pale and cloudy instead of clear. When this fresh, cloudy water reaches the open ocean, it meets salt water that's completely different. Ocean water is packed with dissolved minerals that make it significantly heavier than fresh water. The density difference is so great that the two types of water can't easily blend together. The light glacial water can't sink through the heavier salt water, so it spreads across the surface instead, riding on top like oil floating on vinegar. At the point where they meet, a sharp boundary forms because the fresh water is trying to spread outward while the salt water is pushing back from below. Scientists call this kind of boundary a halocline, which means it's created by differences in salt concentration. Even though there's nothing solid there, the density difference acts like a physical barrier that keeps the two water masses separated. Salt creates one type of boundary, but temperature creates another kind that works the same way. Cold water is denser than warm water because the molecules pack together more tightly when the temperature drops. When freezing currents from polar regions meet warm currents flowing up from the tropics, the two masses behave like entirely different substances. The warm water flows across the surface because it's lighter. The cold water stays deep because it's heavier. Between them forms a sharp boundary where the temperature changes dramatically across just a few centimeters of distance. If you were diving and passed through one of these boundaries, you would feel the change instantly. One moment you're swimming in comfortable warm water where visibility is good and your body feels relaxed. The next moment, without any gradual transition, you drop into water so cold it takes your breath away. This kind of boundary is called a thermocline. It can be so stable that submarines use it for tactical purposes. A submarine can settle onto a layer of dense cold water and shut down its engines completely. The vessel will just sit there, balanced on the temperature difference like it's resting on an invisible shelf, neither sinking deeper nor floating back up to the surface. At the southern tip of South America, where the continent narrows to a point at Cape Horn, the Atlantic Ocean meets the Pacific in a passage called the Drake. This is one of the most violent boundaries between oceans anywhere on Earth. The water here never stops moving because massive currents from two different oceans are being forced together in a relatively narrow space. The boundary doesn't look like a clean, straight line. Instead, it's a zone of chaos that can stretch for dozens of kilometers. Waves from different directions crash into each other. Fog forms where warm air flowing over one ocean meets cold air coming off the other. Ships crossing through report that everything changes when they cross from one side to the other. The vessel starts rolling differently because the water density has shifted. Air temperature can drop 10 degrees in minutes. Crew members go from sunshine to freezing wind just by crossing an invisible line. Sailors describe it as moving between two different climate zones. On the Atlantic side, conditions might be manageable. Cross into Pacific water, and the ship enters an entirely different environment. This happens because the two oceans have different temperatures, different salt concentrations, and different current patterns. When they collide in a confined space, the interaction creates weather systems that wouldn't exist if either ocean was there alone. The Strait of Gibraltar shows how these boundaries can work in 3 dimensions, instead of just across a horizontal surface. The Mediterranean Sea sits surrounded by hot, dry countries, where water evaporates from the surface faster than rain and rivers can replace it. This makes the Mediterranean gradually saltier over time, and all that extra salt makes the water heavier and denser. When this heavy Mediterranean water flows westward and reaches the narrow strait that connects to the Atlantic Ocean, it can't stay on the surface anymore because it's too dense. So it sinks below the lighter Atlantic water and flows along the bottom of the strait in the opposite direction from the surface current. This creates a remarkable situation, where the strait has 2 separate rivers of water flowing through it at the same time, stacked on top of each other and moving in opposite directions. On the surface, lighter Atlantic water flows east into the Mediterranean to replace what's evaporating. Underneath, heavy Mediterranean water flows west out into the Atlantic. Sailors figured this out hundreds of years ago, long before anyone understood the science behind it. When they wanted to sail into the Mediterranean against the prevailing winds, they would lower a weight or a drogue deep into the water on a long rope. The bottom current would catch it and drag the ship through the strait, even though the surface current and the wind were both pushing in the opposite direction. If you stand on the cliffs overlooking Gibraltar and look down at the water, you can actually see where this boundary exists. The Atlantic water looks darker and deeper blue. The Mediterranean water looks lighter and more transparent. The line between them is sharp enough that it looks like 2 different liquids were poured into the same container and refused to blend. Off the southern coast of Africa, at a point called Cape Agulhas, the Indian Ocean meets the Atlantic in a way that's different from any other boundary. The warm Agulhas current flows down from the Indian Ocean carrying tropical water. When it meets the cold Atlantic water, the result isn't a clean line. Instead, you get massive swirling patches of water in different colors. This boundary is dangerous because it creates what sailors call rogue waves. These are walls of water that can rise 30 meters high and appear without warning, even on calm days. They form when 2 different water masses with different densities collide. The collision also creates huge eddies, hundreds of kilometers across, that break away and drift into the opposite ocean. Inside them, the water maintains its original temperature for months as it travels, carrying fish and organisms that don't belong in that region. Ships crossing this boundary report air temperature changes of 10 degrees in half an hour. Dense fog forms where warm, humid air meets cold, dry air. It feels like sailing from summer into winter just by crossing an invisible line. These boundaries don't just separate water. They also create borders for ocean life that are as real as any coastline. Many species of fish and marine mammals spend their entire lives on one side of these boundaries and never cross over, not because there's any physical barrier stopping them, but because the water on the other side has chemistry their bodies aren't adapted to handle. Plankton, which are the microscopic organisms that form the foundation of every ocean food chain, are extremely sensitive to both salt concentration and temperature. Different species have evolved to thrive in different conditions, so the plankton living on one side of a boundary are often completely different species from the plankton on the other side. The small fish that feed on that plankton stay where their food source is. The larger fish that hunt those small fish stay where their prey lives. An entire ecosystem organizes itself around an invisible line. In the Gulf of Alaska, you can watch schools of fish swim up to the boundary between dark water and light water, and then turn around without crossing it. They'll swim parallel to the line for kilometers, but they won't go across. The chemistry on the other side is wrong for everything their bodies need. Some larger marine mammals use these boundaries tactically. A whale being chased might suddenly dive across a thermocline, plunging from warm water into freezing cold. The whale can tolerate this shock because it has thick blubber, but the sudden temperature change can disorient the predator enough that it breaks off the chase. For ships, these boundaries create practical problems that go well beyond just being visually interesting. When a large vessel crosses from one water mass into another, the density of the water underneath the hull changes suddenly. This changes how deep the ship sits in the water, and the adjustment happens so quickly that people on board can feel it. Captains report their vessels rising or dropping several centimeters at the boundary. The hull makes groaning sounds as the forces shift. Down in the engine room, the machinery sounds different because the propeller is suddenly biting into water with different resistance. On the bridge, the autopilot system can get confused because it's programmed for consistent water conditions. When the density changes, the ship's handling changes. The autopilot overcorrects, the ship drifts slightly off track, and the officers have to manually adjust until the system recalibrates. Sonar equipment has even more serious problems. Sound travels at different speeds through water, depending on temperature and salinity. When the ship crosses a boundary where those conditions change sharply, the sonar readings become unreliable. Sometimes the equipment will show what looks like solid rock directly under the ship, even though the charts indicate open water hundreds of meters deep. The sound waves are hitting the density boundary and reflecting back, the same way sound bounces off a solid surface. Sailors call this a phantom bottom. The sonar image looks completely real. The equipment is working perfectly, but the obstacle it's showing doesn't exist. Looking at these sharp, visible boundaries, it's natural to think they represent permanent walls that keep the oceans completely separated forever. But that's not actually what's happening. Beneath the surface, at a pace too slow for humans to observe directly, water molecules are constantly crossing these boundaries in both directions. The process is called diffusion. Molecules in any liquid are always moving randomly, bouncing off each other and gradually spreading out. In the ocean, this happens incredibly slowly because the forces keeping the boundaries stable are so strong. A single molecule of salty water might take decades to drift across into fresher water. A molecule of cold water might need a century to rise through warmer layers. But the movement never stops. Deep below the surface, far beneath the visible boundaries, there's a global circulation system that connects all the oceans. Warm water from equatorial regions slowly travels toward the poles. Cold water from the depths slowly rises toward the surface. Over thousands of years, water from the Pacific ends up in the Atlantic. Water from the Indian Ocean reaches the Arctic. If you could mark a single drop of water in Alaska and track it across centuries, you would eventually find that drop on the other side of the world. The boundaries we can see aren't permanent walls. They're temporary delays. The mixing is happening constantly. We just can't observe it, because it takes place over time frames longer than human lifetimes. This creates an interesting situation where the answer to "do these oceans mix" depends entirely on what timescale you're measuring. On a human timescale, measured in days or years or decades, the boundaries are completely real and stable. The line in the Gulf of Alaska has looked the same for as long as anyone has been recording it. For any practical purpose, those oceans are not mixing. But on a geological timescale, measured in thousands of years, the boundaries are temporary and porous. Water crosses them constantly. Given enough time, the entire system becomes one unified body where molecules have thoroughly blended together. When people say these oceans never mix, what they really mean is that the mixing happens so slowly, you will never witness any change in your lifetime. The line will look exactly the same tomorrow as it does today. It will look the same next year. It will probably look the same 100 years from now. But it's not the same as never in the absolute sense. The line is real and temporary at the same time. It just depends on whether you're measuring time in years or in millennia. What looks like permanent separation is actually extremely slow mixing. What looks like a solid barrier is actually a delay mechanism. And what looks stable is actually fragile, dependent on specific balances that could shift if conditions changed. The oceans meet, but don't mix. Except they do mix, just not in any time frame that matters to the people watching from the deck of a ship.